this lecture will be on the X-ray imaging system, and you have some objectives that you are going to have to be able to answer, so make sure you review them and are able to answer them so you can do well on your exam. All right, so there's a lot of different types of X-ray equipment. So the two main types, there's therapy and there's diagnostic, okay? So within diagnostic, that's what you guys are doing is diagnostic X-rays. Therapeutic is like radiation therapy, okay? It can include nuke med in there also. So in diagnostic, I guess nuke med could cover over diagnostic too, right? So we help diagnose with nuclear medicine, but it's a little bit different so than X-ray. So with diagnostic, we have diagnostic ranges, and we go anywhere from 10 to 1200 milliamps, okay? And we can get 001 to 10 seconds in length on our exposures. So we also have KVP ranges that can be anywhere from 20 to 150 kilovolts peak, okay? So that's as high as we can go is the 150 within our diagnostic range. So looking at the X-ray machines, as you can see here, we have a just a general purpose X-ray room with the table, and here we have a C-arm. With the C-arm, we need to have monitors also, okay? So let's talk about the X-ray tables. They need to be uniform, radiolucent surface, okay? So there can't be pockets of more dense areas. So typically they're made of carbon graphite, and we use the carbon graphite because they don't absorb photons as much as other materials, okay? We also like the carbon graphite because they're easy to clean and they're free of crevices that could collect contrast material. So when you're doing a barium enema and you lose your contrast, so what happens is it gets in the cracks and then sometimes you can't get it out. It's too deep, okay? We also like the carbon graphite because it's difficult to scratch. So you can go ahead and go in your X-ray room in clinic and try to scratch the table with your fingernail. You can see it's really, really hard to scratch it, okay? These X-ray tables have a bucky tray typically. Some of the units have built-in DR plates in them, but most of them have a bucky tray where you could load a CR or DR or even film cassette. All right, so there's fixed and tilting tables, okay? They can tilt or shift or tilt or head to toe is what I'm trying to say. So you can go 90-50 tilt, you can do a 90-45 or a 90-90. So 90 degrees in one direction and 30 degrees in the other direction is most common. Most of the tables have a footboard, and what we do is we put the footboard on when we're doing any kind of GI study where we're going to have to stand the patient up. So we'll put the footboard on. Now, a lot of times I will actually use the footboard in an X-ray room when I have a little frail person or someone who's really weak and they came in a wheelchair and I can't slide them over from gurney to table. I'll actually put the footboard on and I'll stand the table up, lower it all the way down, and then stand the person up and stand them up on the footboard and then lay the whole table down. Okay, so that's another way for you to use that footboard to your advantage. So if you see someone that's really struggling, they're super weak and they're in a wheelchair, that's an easy way to get them up on the table rather than trying to get them up on a step and up onto the table, okay? So there's shoulder supports and hand grips. So we use the shoulder supports when we do a myelogram. So we actually tilt the table towards the head down, and we use these shoulder supports to help keep the patient on the table and from sliding off and landing on their head. Always makes me very nervous, and I check the tightness of those 1,000 times, and I'll actually stand at the head of the bed, and sometimes I'll hold the braces just to make sure if the patient's got some girth to them. So I get nervous. I don't want them sliding off and landing on their head. It'd be terrible. So there's also compression bands that can be clipped to the tables, okay? They have 3 functions. So one, they restrain a patient. Now, legally, this is kind of a gray area. We're not supposed to restrain patients with our compression bands. If you're by yourself at 3 in the morning and the person has seizures, you're going to want to use a compression band to help keep them from falling off the table. The thing is, it's false imprisonment, so they have to be able to get out of it. So be careful when you're using any kind of compression band as a restraint, okay? We also use it to compress abdominal tissues. If the patient is pretty heavy, we'll use a compression band, so that helps reduce dose to the patient and helps reduce scatter. So we will compress the abdomen with these compression bands. We'll also use compression bands to compress the ureters when we're doing any kind of IVP or IVU study, so that we can see the kidneys fill up with contrast, which is really nice. Gives us a beautiful study. So this is an example of a fluoroscopic couch or table that we would tilt 30 degrees towards the head, so you can lower the head down 30 degrees. And as you can see, that's pretty steep. So we'll have these shoulder harnesses on here holding the shoulders to keep the patient from falling and sliding off, because the tables are pretty slippery. We can also stand it up 90 degrees. You can put the foot pedal on so that you can get patients on, and we can do standing views for patients. Here is a floating table, so sometimes they're motorized, which is really nice. Most of the time they're not, though, so you just have to manhandle them, and we'll use these with C-arms quite a bit. All right, so table supports, there's a lot of different configurations. There's overhead, floor to ceiling, and floor. So if you see the overhead, you can see it's attached on rails overhead. So these are the easiest to use. I love these overhead units, super, super easy. So it's a ceiling suspension, and it allows for longitudinal, transverse, and vertical movements, and it detents or has centering locks for you to either lock on the table or lock on the upright bucky. There's these, here we have the floor ceiling mount actually here, so you can see it's mounted, so it slides on rails, and usually the upright bucky is aligned with the table, so you can't do much going side to side. So here, this is a floor mount, so it's not attached to the ceiling. Okay, so if it had a bracket up here, it would be floor ceiling, but it doesn't, so it's just floor mount. Okay. Okay, so there's mobile and there's C-arms also. So mobiles are mounted on the floor, and as you can see here, we've got a whole base unit and an arm like a giraffe's neck that comes out, and we can position for the patients. Then we have a C-arm where it's locked on a C. So this is a C, so we call it a C-arm. So these C-arm devices usually have a monitor, and they're used for fluoroscopy. So this right here is a dual floor mount. So we have floor and ceiling mount. So we have two C-arm units that can work simultaneously to help reduce dose and contrast for patients, as we can see AP and lateral at the same time. It's pretty cool. Really fun to drive. Boy, you have to be on your toes. All right. So upright receptor unit, so supports image receptor in the vertical orientation. It has a bucky assembly, and it has AEC typically built into it. It travels up and down, so vertical, and it can tilt or non-tilting. So we can actually tilt these buckies. So those are pretty cool. I see them a lot at Kaiser's because they do a lot of sinuses. So they'll tilt the bucky instead of tilt the patient. So that's good. Numerous uses. Number one reason that we have an upright bucky is for chest. We do upright abdomens all the time, AC joints, C-spine, standing orthopedics, sinuses, all of that. So very, very popular. So other specialized diagnostic equipment, we have mammography, which has a specialty unit. We have tomography, which is, we can have tomography within mammography, or we have tomography within a general x-ray room. And what tomography means is that the tube is going to swing from head to feet or feet to head, okay? And it's going to take a slice, you can program it to however thickness you'd like. So if you want a 1 centimeter slice at the level of 6 centimeters off the table, so it gives you a good slice of the kidneys. Okay, so we use it in breast imaging. It gives us 3D breasts, which are the new latest greatest thing, and everyone's going to it. So we have in dental x-rays. So they have an x-ray unit, or they have what's called a nomad. So I don't know if you've ever heard of a nomad. It looks like a radar gun. It's handheld, and it can take x-rays. Pretty cool. Then there's a panoramic unit that actually moves all the way around the patient's head. Well, 180 degrees around the patient in the front. Okay, so does a great job on mandibles. Pretty cool. We also have computed tomography, which is using an x-ray tube, and it has rows of detectors that intercept the radiation, and it spins around the patient at a very high speed. There's radiation therapy simulators. So the simulators help with radiation planning. So they can see exactly where the tumors are, and it's a different table that they use. So pretty cool. And then urologic. So up in the OR, a lot of times they'll have a urology suite, and in the urology suite, they'll have a specialized table that is used for urology studies. So typically it's not a fluoro unit. A lot of them are putting in fluoro units now, but we used to just take still images, so it'd just be x-ray tube, but it's a specialized table, and the way that you have to get the images is different. Okay, so those are the specialty areas and equipment. All right, so let's talk about power. Power. So as you know, power here in the U.S., we have incoming line currents at 60 cycles in the U.S. 50 cycles is worldwide, so we go from 220 to 240 volts, and we have 440 to 480 if we're on 3-phase. Okay, so single-phase power is inefficient in X-ray production. 3-phase power is most popular and widely available. So incoming line current, let's talk about this. So power is called incoming line current, and incoming line current and mains, and is supplied at 3-phase power cycle. Awkward sentence. One half of the wire is called above ground, and the other is below ground potential, with each varying 110 to 120 volts. Okay, so US is 60 hertz on AC. AC is alternating current. So the two hot wires reverse the polarity 120 times per second. Okay, these sound like great quiz questions. Okay, the two lines are not in phase with each other. Okay, results in about 210 volts. So if we look here, we have 60 hertz of alternating power. The root mean square voltage is 200 to 240, and nearly all X-ray equipment operates on 210 to 220. So as you can see here, 120, 120 for a total of 240. Okay, you can see this is a step up. All right, so single-phase power, the potential difference drops to 0 with every change in direction of the current. So it's 70.7% of the peak kilovolts. So if you put in 100 kilovolts that you're looking for, it's only going to give you 70% of that. So basically about 71 kVp instead of your 100. Okay, so if we look at full wave, the X-ray tube is experiencing no potential difference, producing X-ray photons 120 times each second on a 60 hertz line. All right, so here we have single phase power. So A is incoming line current, so this is a good sine wave. So as you can see, the solid line is the positive, the dotted line is the negative, right? So if we look at B, this is a full wave rectified sine wave. So you have this portion, so this portion down here is flipped up here. Okay, so 60 hertz line, an exposure of 0.1 second with a single phased full wave rectified unit results in 12 intervals of no photon production. So this is where you're dead right here. There's no photon production. Okay. Multi-phase power. So 3-phase power produces very low voltage ripples. So most efficient type of electrical power, and it's used with high-end electrical devices such as X-ray machines. So as you can see here, we have phases. So you can tell by the color. So we have a sine wave right here of blue. Then we have a sine wave right here of the yellow. Then we have a sine wave right here of the, I don't know what color that is, salmon. So you can see that we have 3 phases going on at the same time, okay? So down here, if we increase our phase, you can see we're getting more ripple, so they're not as deep, okay? So a basic X-ray unit. So the main X-ray circuit is the high voltage side of the circuit. It has the exposure switch and the timer switch. On the filament circuit, it's the low voltage side of the circuit and provides current and voltage to the filament, and it permits selection of milliamps. The exposure switch is a dead man switch. What does a dead man switch mean? So what that means is if you're taking an X-ray and you have rotored up and you're ready to expose and you drop dead, you are going to let go of that switch when you drop dead. Okay, so you're not going to, if you die while you're holding it, you automatically let go of everything when you die. All your muscles release. So it's called a dead man switch. So if something happens to you, it will stop. Okay, so if you push it, it doesn't just stay forever. You know, it's only reacting to your pressure. Okay, it's located behind the control console window on a general console, and what the state of California has done is they actually make us adhere it to the console so that you can't walk into the X-ray room while you're taking an exposure. Okay, so if you go to your clinical site and your exposure switch is not adhered in some way to your control console, it's a Title 17 violation. So when I go in, I do site visits, I'll actually zip tie those together just so that you guys trying to save the site from getting a violation. Kind of crazy, huh? You need to depress the switch down, so the exposure switch, in one full motion. Okay, so there's a 2-step process. If you go down halfway, then you'll rotor up. Okay, and you start boiling off all of your electrons. And then when you go all the way down, you apply the potential difference, which is going to shoot those electrons across your tube to produce your photons. So what happens is, if you go all the way down before the tube was ready, it wouldn't shoot properly. It wouldn't give you your full amount of photons, okay? They fixed that. So in the modern equipment, you can just push it all the way down. So no 2-step process, all the way down in one swift motion. And soon as it's rotored up to speed and has enough electrons, it will automatically shoot. Okay, so you're going to wear out your rotor and your tube by holding down halfway before you expose. Okay, so you're wearing out the tube. All right, so there's a separate anode and rotor switch are also used, so we'll actually prep that. So we'll go down halfway if we have a kid, right? So you have a kid and he's squirming all over the place, or you have a baby and you have them in a picostat and they're screaming, and you're rotored up until they go to scream again, and then you hit it. So as soon as they take that full deep breath, then you expose. But you want to prep and make sure that you're ready. Those are the only times that you should be using your prep or your rotor button, okay? So the other thing that's important to know is that your mobile equipment, so all of your C-arms and your portables, require a 6-foot cord, okay? And we talked about that because of the leakage radiation coming out of the lead housing. So remember what that is? It's 100 MR at 1 hour at 1 meter. So you need to make sure that you are 6 feet away. So that exposure cord will be 6 feet. All right, the timer circuit. So it regulates the exposure termination. We use electronic timers as they're most sophisticated. It's capable of very short exposure times, which is great. Your MAS timer terminates exposure based on the predetermined MAS value, and there's an AEC timer also. So X-ray imaging system components, there's 3 main components. It's a great quiz question or exam question. There's the operating console, the X-ray tube, and the high voltage generator. Okay, so this is the imaging system components. The operating console allows the technologist to control the X-ray tube current and voltage. So tube current 100 to 1200 mA is common, and the voltage 25 to 150 ensures the useful X-ray beam is of proper quantity and quality. Okay, so radiation quantity talks about the number of photons, and it's equal to the X-ray intensity. So you hear us talk about intensity. Intensity is quantity. Intensity is quantity and mass. Okay, so if we're talking about quality, so radiation quality, which is our X-ray penetrability, we're talking about our KVP. Okay, so KVP is X-ray penetrability and our quality. Now we can refer to it just as intensity and penetrability, and you should know that that is KVP and mass. Okay, we can say your quantity and your quality, and you need to know your quantity is your mass and your quality is your KVP. Okay, so make sure that you know these inside and out and you don't get them confused. All right, so quantity versus quality. So quantity, X-ray intensity refers to the number of X-rays in a beam expressed in milligrays or milligrays over ampere per second. We have the quality, which is the X-ray penetrability. So it's like the energy or the force of the X-ray beam. Okay, it's expressed in kilovolts peak, or more precisely, half value layer. Half value layer is the way that we measure KVP. Okay, so we'll talk about KVP and half value layer. They always go together. Okay, so always, if you are wondering, oh, like if I ask you a question about half value layer, what are we measuring? We're measuring KVP. What's KVP? Quality. Okay, so if I'm talking about how do we measure the quality of the beam, so you know quality is KVP and KVP is linked to half value layer. Okay, so we measure half value layer with the quality of the beam to see the quality. Okay, so don't get that wrong. Operating console provides control of line compensation, KVP, MA, and time. So electric circuits operate at low voltage to avoid hazardous shock, so you don't get shocked. So the console is on the low voltage side of the circuit. So if we look here, this is an operating console circuit diagram. Okay, you should recognize this thing. So it's not the whole thing. As you can see, our rectifiers aren't on here. So we've got our KVP major and our minor, and we've got our meter, KVP meter right there. We've got our timing circuit. Here's our MA meter. And down here is our MA selector, which is a rheostat. All these are, this is our auto transformer, has an iron core. Remember all that line current coming in at 60 hertz. And then we have 220 to 240 volts coming in. We have a line monitor to make sure that the incoming line current is correct. Now, if it's not, we've got this line compensator right here. Okay, so it's going to make up, this is going to tell this to work together to figure out and make sure that it's getting the correct amount. Okay, it's going to make sure it's at 220 volts. Okay. So the high voltage generator converts the low voltage supplied from the power company to high voltage required to produce X-rays and high amperage to the milliamperage needed to produce the current to the filament. There are three parts to a high voltage generator. There's the high voltage transformer, the filament transformer, and rectifiers. All right, so generators. There's single phase, there's multi-phase, three-phase. There's high frequency. Okay, now there's three phase, there's 6 pulse, there's 12 pulse, there's different multi-phase. They talk about three phase a lot. Okay, there's also a capacitor discharge, and we use those in our mobile units. Okay, we have battery operated mobile units, and we have falling load generators. Okay, so those are all different generator types, and we're going to talk about each one. So unrectified voltage. So rectification is essential for safe and efficient operation of the X-ray tube. The voltage waveform appears as the voltage waveform supplied to the primary side of the high voltage transformer, except its amplitude is much greater. Okay, so you can see here we've got our sine wave, right? Here's our sine wave. So we rectify this. So we take this and just here, we're just wiping it out. It just disappears. So we have a wave, nothing, a wave, nothing, okay? So half-wave rectification contains 0, 1, or 2 diodes, produces 60 X-ray pulses per second. The disadvantage is we waste half of the power supply, requires twice the exposure that we normally would use. So we're taking it and we're just rerouting it. So it's not negative, it's not going down negative, we're just taking it and making it go straight, okay? So we're not doing anything but just wiping out that negative part of the beam, okay? So half-wave rectification, a condition in which the voltage is not allowed to swing negatively during the negative half of the cycle. So rectifiers convert alternating current to direct current to operate the X-ray tube. So the positive portion of the AC waveform allows electric current to pass through the tube. The negative portion of the AC waveform, the rectifier does not operate, no current is allowed. Okay, the result is a series of positive pulses separated by gaps where the negative current is not conducted. Okay, so if we look here, single phase produces 100% voltage ripple. So we go from 0 to 100 to 0. Okay, so we stay, so we have voltage ripple. It goes all the way down from 100 to 0. Okay, back down to baseline. So most efficient X-ray production occurs during the portion of the voltage waveform. So if we use rectifiers, we're coming here, we have 100%, so 100 back down to 0, okay, 100% voltage ripple. But we've taken the negative portion right here and we've rectified it to give us only positive. So we're not losing this portion of the beam, okay? We are getting a pulse, we're flipping that negative up here, okay? That's with rectifiers. So single phase generators are still on them. Now we have fully rectified units. It's 2 pulses per hertz, so 120 pulses per second. The voltage ripple is 100%. So this is it. So we've taken it and we've rectified it. So that negative portion is flipped up. Okay, so rectifies the entire AC waveform, contains at least 4 diodes. So negative half cycle is reversed, anode is always positive. Exposure time for any given exposure is cut in half and produces 120 X-ray pulses each second. So results in a pulsating X-ray beam. Voltage alternates from 0 to a maximum potential 120 times each second under full wave rectification. X-rays produced when the waveform is near 0, their little diagnostic value. In order to compensate for this rise and fall in the current, 3-phase power is used. All right, so half wave versus full wave. So we have half wave rectification, so you can see we just took out that negative wave, and then we have full wave where you can see we flipped up that negative portion. Instead of just losing it, we flipped it up, okay? So full wave rectification with 6 diodes. So there's 6 pulses per hertz, 360 pulses per second. The voltage ripple is 13 to 25%. Oh, that's pretty good, huh? So multi-phase power, 3-phase power, is produced by the generator and is how it's supplied from the power companies. So each peak begins to drop to 0. The overall potential difference is boosted back by the peak of the next phase wave. So it never drops to 0 and you've got a very small ripple, okay? So full wave rectification, the net voltage produces a voltage ripple, okay? Because we're not going to 0. All right, so 3 waveforms are provided, so the resulting waveform maintains a nearly consistent high voltage, never dropping to 0 during the exposure. There are 6 pulses per 1/60th of a second compared to 2 pulses of the single phase power. Limitations to the speed of start of an exposure, so the initiation time. So the initiation time and extinction time, okay? So initiation time is how long it takes for you to start the exposure, and the extinction time is how long it takes to end the exposure, okay? So both are limited with this, and the principal disadvantage is money. Everything comes down to money, right? All right, so We have full wave rectified units with 12 diodes. Oh my goodness. So we have 3, 6, 12. Okay. So we have 12 pulses per hertz. We have 720 pulses per second. We have a voltage ripple of 4 to 10%. That's fantastic. Much better. So if we take a look, we have single phase power. We have three-phase power. We have 3 different phases going on at the same time, which gives us a ripple, right? So we have 3-phase. So here's single phase. We have single phase 2 pulse. We have 3-phase 6 pulse. So if you counted 1, 2, 3, 4, 5, 6, so there's 6 pulses. Here we have 3-phase 12 pulse. So you can see here we've got 12 pulses. And you can see 100% voltage ripple, 13% voltage ripple, 4% voltage ripple. So not bad. So 4% with our 12 pulse. Okay. So you can see here 3-phase 6 pulses right there. All right. So you can see the drop from here to here. That's our drop. Okay. That's our ripple. So you can see here the ripple is very small. All right, so AC and DC power converts and inverts. So 60 converts 60 cycles to kilohertz. So a full wave rectified unit can produce 12 to 13 kilohertz waveforms. Voltage ripple is 3 to 4%. Most popular and common type of generator, most efficient. So it's only a 3 to 4% ripple, which is really small. This is what all of our generators are now. So pretty much everywhere you go, there's high frequency generators, okay? So it's very, very little voltage ripple, as you can see here. So the drop is very small, okay? So produce nearly a constant potential waveform, improving image quality at lower patient doses, uses 500 to 25,000 pulses per second, used in most modern X-ray systems and mammo units. So when we dial up and we want, let's just say 100 kVp, we're only losing just a few percent compared to 100%, right? Or 13% or 25%. So we are doing really good. That's what we're using nowadays. So if we look here, variations in the 2 voltage during exposure. So lower voltage ripple has the highest radiation quantity and quality. So the percent of ripple is the voltage fluctuation. So that's our kVp fluctuation. So as you can see here, we go from 100 to 0. Here, then that's half wave. Full wave rectified, we go 100 to 0. Then we go 3-phase 6 pulse. We have a 14%, okay, that we're losing. We're losing 14%. So we get, if you have 100 kVp, you're looking at 86 that you are going to get as your peak, okay, kVp. So here, this is 3-phase 12 pulse, and this has to do with how many diodes you got, okay? So if we're looking here, we're at 4%. So that's not bad. And then if you look at a high frequency, we're at less than 1%. So this would be like a 96 kVp and this would be a 99. So we always want to use a high frequency generator. So here is another graph. So rectification type, we have half wave, full wave. We still have 100% ripple. And if we go 3-phase 6 pulse, we're at 14, 3-phase 12 pulse 4, and a high frequency 3-phase is less than 1%. And this is just another picture, let you see what it all looks like. So same thing, same thing. So all the numbers, they fluctuate just a little bit, but overall they're saying the same thing. Okay, capacitor discharge mobile units requires pre-charging a large electrical capacitor. Okay, do you guys remember what a capacitor looked like? It had 2 plates looking at each other and then they charge up and then you're able to discharge them, okay? So you have to plug them in all the time. So we'll use portables with this. Produces a current wave tail after exposure termination. This delivers a low RMS voltage and lower output. Typically uses a grid-based X-ray tube. So as you can see here, we charge it up, we're ready, and then we start the exposure and then it falls here, okay? So this is a capacitor discharge unit. This is what this is called, and this is the graph that it looks like, okay? So Operates by charging a series of silicone-controlled rectifiers from the direct current of a battery. So, battery. During exposure, the charge is released, forming an X-ray tube current needed to produce X-rays. Precise radiographic technique is needed. The problem is you end the exposure and sometimes you still have some leakage. So it doesn't shut off completely right away. Okay. So battery-operated mobile units used for portable radiography. So onboard batteries, yes, they're rechargeable and they require to be plugged in. We can unplug them to expose and drive. Supply non-pulsating direct current, so similar to three-phase 12 pulse, and the output is very efficient for X-ray production. So low kilowatt output limits the use of mobile studies, so we can't get real high kVps, okay? Falling load generator. So here, exposure begins at max MA and drops as the anode heats. So results in minimum exposure time, causes the kVp to fluctuate throughout the exposure, and can shorten the tube's life with consistent use of high MA. So this one is here. So as you can see, here's our time. This is our MA. So here we're going to go and we're going to drop off. Okay, so you can see falling, right? So the highest MA setting at the shortest possible exposure time. Initial tube loading is high and drops during the exposure. So you don't get a consistent amount of radiation coming out at the same time. So it's coming out high and dropping as it goes, okay? So it's used in like IR. All right, let's talk about power rating. So transformers and high voltage generators are identified by their power rating in kilowatts. So power is current times potential, and watt is amperes times voltage. So this assumes a constant current and voltage, which does not exist in single phase X-ray systems, right? Because it's 100% voltage ripple. All right, so high voltage transformer. There's a step-up transformer where the secondary voltage, kilovolts, is higher than the primary voltage, okay? So we've talked about these before. So the primary current in amperage and secondary is milliamps. So we come in with amps and we come out with milliamps because there's got to be give and take, right? So if you're going up in kVp, you're going down in your MA to MA. So the number of secondary wiring is that of the primary windings. This relationship is called if there's a difference, it's called the turn ratio. So the turn ratio, 500 to 1 or 1,000 to 1, the voltage increase is directly related to the number of turns there are, so the turn ratio, okay? Only operates in alternating current. So you could solve this. As you can see, we have a formula here. Voltage primary, or it would be voltage secondary over voltage primary, is equal to the number of turns secondary over the number of turns primary. So easy to solve. We don't have you solve those anymore, but it's there for you. So voltage rectification. It's the process of converting alternating current to direct current for the X-ray tube. So a wall plug is 60 Hertz of alternating current. The current changes direction 120 times each second. Okay, ensures electrons flow in only one direction in the X-ray tube from cathode to anode. Okay, that's what we use our rectifiers for. Is we have this alternating current and we need to make sure that we're going from cathode to anode only. Okay, reversal of electron flow would cause the damage to the X-ray tube because the design cannot withstand the heat. Okay, the cathode would break. So is achieved through the use of diodes, and we typically use solid state diodes. There's also vacuum tube rectifiers, but solid state is what we use today. All right. So rectifiers in most modern X-ray generators are solid state and made of silicone. They're considered a semiconductor. The multiple black components on this multiplier board are rectifiers. So all of these little pieces right there are rectifiers. So this is what a symbol is for a rectifier. This is a solid state rectifier. As you can see, the current is heading that way. So diodes that conduct electric current in only one direction. The arrow points in the direction of the conventional electric current flow. Okay, so diodes are found on the high voltage side of the transformer. So let's talk about the autotransformer. It is the power supplied to the X-ray system is delivered first to the autotransformer. It works on the principle of induction. So electromagnetic induction, an electrical current is induced in a circuit if some part of that circuit is changing magnetic field. So on one of the test questions we had was if there is two items, let's say an autotransformer and a bar magnet, and they're traveling next to each other exactly the same, do we induce a magnetic field? And the answer is no, we don't. One has to be changing. So there's got to be a change, okay? So if they're doing exactly the same thing, there's no change, therefore there's no electromagnetic induction, okay? So it has a single winding and is designed to supply a precise voltage to the filament circuit and to the high voltage circuit of the X-ray imaging system. That's the goal of the autotransformer. A lot of them have an iron core, so don't be surprised. So if we look here, it's just talking about A and A with asterisk. So it conducts the input power to the autotransformer. It's called the primary connections. So these are the primary connections. Then we go to C up here, is located close to the end and allows the autotransformer to increase voltage. So D and E allow a decrease in voltage, D and E. So this is where we're talking about our KVP minor and major, okay? So C, D, and E are secondary connections. So the autotransformer law, so autotransformers is an induction device. So the voltage it receives, primary voltage, and the voltage it provides, the secondary voltage, are related directly to the number of turns in the transformer enclosed by the respective connections. So you can see voltage secondary is equal to the number of turns secondary, and voltage primary is equal to the number of turns primary. So if you need to solve, it's the same thing as the inverse square law, but no square. So use cross multiply and divide. Excuse me. All right. So we look here, we got the KVP control. So KVP determines the quality or penetrability of the X-ray beam. So there's KVP minor and major. A combination of major and minor KVP gives the appropriate KVP readout for an exposure. So KVP meter is a read voltage and not KVP. Pre-reading KVP meter allows voltage to be monitored before an exposure. So you can see the meter right there. MA control, so X-ray tube current measured in MA. It controls the number of electrons crossing from the cathode to the anode. As the temperature increases, more electrons are released via thermionic emissions. So thermionic emissions is the release of electrons from a heated filament. Their space charge effect is eliminated by a correction circuit, okay? So the X-ray tube current is controlled through a separate circuit called the filament circuit. MA control. The product of the X-ray tube current, MA, and exposure time is MAS, which is also electrostatic charge. So if an image is made at 400 MA and an exposure time of 100 milliseconds, express this as MAS. So it would be 40 MAS. The filament circuit controls the X-ray tube current. It receives voltage from the autotransformer. So precision resistors ensure voltage received corresponds to the selected MA. Okay. MA meter, so monitors the X-ray tube current, connected at the center of the secondary side of the high voltage step-up transformer. So the secondary voltage alternates at 60 Hertz, so no part of the meter is in contact with the high voltage. So we've got the filament transformers. So MA selector, it's a step-down transformer. KVP decreases and MA increases. So you can see the number of windings, okay? It's based on the number of windings. Exposure times, separate from other main circuits, has a device that works to make and break high voltage across the X-ray tube, usually on the primary side of the high voltage transformer where the voltage is the lowest. So there's a guard timer, which is a backup timer that will terminate an exposure after a prescribed time, usually not longer than 6 seconds. Okay, so there's a guard timer, there's a backup timer. Types of timing circuit. There's synchronous timers, electronic timers, mass timers, and AEC, or automatic exposure control. So synchronous timers, driven by a synchronous motor which operates at 60 revolutions per second. So it's recognizable because exposure times are in intervals of 60. So 1/60th, 1/20, 1/30 must to be reset after each exposure, so no serial exposures can be performed. So you take an exposure, you have to wait and let it reset itself. All right, so electronic timers, most expensive, most complicated, most accurate. So these are the ones that we like to use. Composed of complex circuitry, allow for a wide range of intervals to be selected and accurate to intervals as small as 1 millisecond. Can be used to make serial exposures so we can rapid expose, so again and again and again like we do for fluoro. So most suitable for interventional radiology. Mass timers. It's a type of electronic timer located on the secondary side of the high voltage transformer, monitors the product of MA and exposure time, and terminates exposure when the desired MAS is reached. Usually set to give the highest MA in the shortest time. Usually found on falling load and capacitor discharge imaging systems also. Okay, so automatic exposure control. And we're going to have a whole day lecture on AEC. Okay, so automatic exposure control. So AEC measures the quantity of radiation reaching the image receptor. So exposure automatically terminates when sufficient radiation has reached the IR. So it shuts itself off. So it measures the amount and terminates exposure. So an ionization chamber is the type most manufacturers incorporate. So a backup time must be 1.5 times the expected exposure, not to exceed 600 mass. Okay, so 150% and not to exceed 600 mass. So located here, you can see your image receptor. So here's your X-ray tube. You have a photon coming. Here's the patient. You have your ion chamber, and then you have your image receptor. So located in front of the image receptor, not after, in front. It's about 5 millimeters parallel plate chamber. So they're radiolucent at correct KVPs. If you shoot an X-ray with a really low KVP, like if you shoot something at like 20, 30 KVP, you'll see the ion chambers where they're at. It's pretty cool. Usually have 3 detectors, okay, that you can choose from, and not used with extremities, distal extremities like hands, wrists, feet, toes, ankles. Typically when you get to about the thickness of a knee, we'll start to use AEC, but you got to make sure that your anatomy completely covers the photocell in which you're using. All right, so photomultipliers and fluorescent screen converts light produced by the screen to electrical charge. It terminates when pre-selected charge is received. An ion chamber, X-rays ionize the cell, and when preset ionization levels are reached, exposure terminates. So that's typically what we use here is this ionization chamber. Okay, so right here. Minimum reaction time. So the minimum amount of time required to terminate an exposure in AEC. So modern minimum reaction time is thousandths, so 1,000th of a second. Employs SCR switching. And I don't know if you saw that here. Oops, one passed. You can see the SCR. So it's a switch. Okay, makes it fast. All right. Oh boy, right? So you should recognize this. If we have incoming wall, we have 60 hertz, right? Or 220 to 240 volts coming in. We have a line monitor to make sure it is that. We have a line compensator making sure it's 220 volts with our auto transformer, right? We have the auto transformer. We have our KVP major selection, our KVP minor selection with our KVP meter. We also have our timing circuit and selector right here. So we have, this is all the console, which is low voltage, all right here. So we have our step up transformer, which is going to raise our kVp and drop our amps, right? And then we have our MA meter. Here's some diodes. You can see a bunch of diodes to make sure that the flow goes through the X-ray tube from cathode to anode. Okay? Coming down here, past our line compensator, you can see we have our MA selector, and we've got our step down transformer. So we're dropping down our kVp and raising up our MA so that we can boil off our electrons. So as you can see here, we can route so that we're going through the X-ray machine from cathode to anode at all times. Here, you should be able to label this, okay? So here we've got our incoming power source, and number 2, we have our, it's kind of a weird spot. This is our low voltage side, this is our secondary side, which is high voltage, and this is our filament circuit, okay? So this is our switch. It's a circuit breaker, okay? So don't be thrown off by that. This is our kVp meter, our kVp selector. Then we've got here our step-up transformer. This right here is our MA meter. Then we have our rheostats, and we've got a resistor, which is our rheostat right here. Then we've got a step-down transformer. So it's kind of a weird diagram. So right here, this is our stator, right, on either side, and this is our cathode and our anode. All right, kind of a funky picture. Looking here, so we have the console or low voltage side. This is our high voltage side. This is our filament circuit. So coming in, we've got a circuit breaker right here. This is our line compensator right here. This is an auto transformer. This is our kVp major with our kVp meter, our timing meter. This is our step up transformer. Now we're in our high voltage side, and our MA meter should be right about in here. It's not showing it. Then we have our solid state diodes, right? And then down here on the low end, we have our rheostat for our MA selector. We have our step down transformer taking our kVp down and our MA up, coming around to our X-ray tube. Okay, so don't make it harder than what it is. There's a different picture, so be able to label all these. You have the incoming line current, so we've got our auto transformer, I've got our kVp meter, our timing control, we've got our step-up transformer, a rectifier, so our MA meter and rectifiers are in here. They always leave the MA meter out. So we have our MA selector, and we've got our step down, and it goes to the cathode. Okay, so here's our anode and our rotor and our stators on the outside. All right, so although they look different, they're all pretty much the same. Okay, this is a real good one for you guys to label because it's got everything laid out exactly how it should be. Okay. But these are all fair game also, so be able to label each one of these. Okay, that's it. That is our lecture for your imaging system from Bushong.